Welcome to Mrs. De Castro's chemistry class for Tuesday, 2nd September 2014. Today we will be looking at Standard 2 of Indiana's Academic Standards for Science, and that is Atomic Structure and the Periodic Table. We will be looking at core standard, describe how the properties and arrangements of the subatomic particles contribute to the structures of atoms. To start with, let us recall our previous lesson. So we have this model of the atom. It's based on the Bohr model, where we have the nucleus. Inside the nucleus, we have the protons and the neutrons, and around the nucleus, in concentric rings, we have the electrons. So the protons we represent as P+. They have a charge of +1 and a mass of 1 AMU. The electrons we represent as E-. They have a charge of -1 and a mass of 1/2000 AMU, and we have described this as negligible. The neutrons we represent as N0. They have a charge of 0 and a mass of 1 AMU. Recall that the nucleus is positively charged, and this is because of the protons that it contains. Now, the electrons are in continuous orbit around the nucleus. They are compared to the planets in the solar system, which are in continuous orbit around the sun. And the atom is electrically neutral because its number of protons is equal to its number of electrons. Okay, we represent an atom with X, A, B, where X is the symbol of the element, A, the subscript, is the atomic number, and B, the superscript, is the mass number. The symbol of the element may be the first letter or the first two letters of the English or Latin name of the element. For example, we have H for hydrogen, He for helium, C for carbon, Ca for calcium, N for nitrogen, Na for sodium, and this is coming from its Latin name, which is natrium. S for sulfur, Si for silicon, B for boron, and Br for bromine. Now note that when writing the symbols of the elements, the first letter is written in uppercase, the second letter, if any, is written in lowercase. Any other way of writing the symbol of the element will be wrong. All right, let us look at some definitions. Proton number refers to the number of protons in the nucleus of an atom. And this is the same as the atomic number. This is also equal to the number of electrons in the neutral atom. Mass number is the same as the nucleon number. It refers to the number of protons and neutrons in the nucleus of an atom. So we have the term nucleons, and this refers to the protons and neutrons in the nucleus of an atom. So that if we want to determine the number of neutrons in the atom, we have to subtract the atomic number from the mass number. For example, if we have carbon C612, This means that carbon has 6 protons, it has 6 electrons, and 12 minus 6 or 6 neutrons. Sodium 1123 has 11 protons, it has 11 electrons, and 23 minus 11 or 12 neutrons. Chlorine 1735 has 17 protons, it has 17 electrons, and it has 35 minus 17 or 18 neutrons. If we were to draw the atoms that we looked at earlier, carbon atom would look like this. So you have the nucleus with the 6 protons and the 6 neutrons, and around the nucleus in concentric rings we have the 6 electrons. The sodium atom would look like this, where you have the nucleus with the 11 protons and the 12 neutrons, and around the nucleus in concentric rings we have the 11 electrons. And the chlorine atom, we have the nucleus with 17 protons and 18 neutrons, and around the nucleus in concentric rings we have the 17 electrons. So question, how are the electrons arranged around the nucleus? We have what we call electron structure to answer that question. And electron structure refers to the arrangement of electrons in the electron shells of an atom. And what are electron shells? These are the fixed spaces in an atom in which the electrons are found. This brings us to what we call electronic configuration, which actually details for us how the electrons are arranged around the nucleus. And this is governed by 3 rules. 1 is the Pauli exclusion principle, 2 is the off-bow principle, and 3 we have the Hans rule. At this point in our chemistry lesson, we will not look at the details of each of these rules, but rather we will look at their implications. So, if we follow those 3 rules, we will come up with a structure like this, where we have the main energy level, and there are 7 of them, 1, 2, 3, 4, 5, 6, 7, each corresponding to the 7 periods in the periodic table. The number of sub-levels or types of orbitals corresponds to the main energy level number. So you have 1 for the first main energy level, 2 for the second main energy level, 3 for the third main energy level, 4 for the fourth main energy level, and so on and so forth. Now, in terms of orbitals, the 1 in the main energy level would be the s, the 2 in the second main energy level are the s and the p, the 3 in the third main energy level are s, p, and d, the 4 in the fourth main energy level are s, p, d, and f, and the 5 in the fifth main energy level are s, p, d, f, and g. We will stop here. We will not need the 6 and the 7 main energy levels with the present elements that we will be working with. So, if we are to look at the number of orbitals, we can have the formula n squared, where n refers to the main energy level number. So, 1 squared will be 1, and that refers to the s orbital. 2 squared is 4, and that refers to the 1s orbital and the 3p orbitals. 3 squared is 9, and that refers to the 1s orbital, 3p orbitals, and 5d orbitals. 4 squared is 16, and this refers to the 1s orbital, 3p orbitals, 5d orbitals and 7f orbitals. And 5 squared is 25. This refers to the 1s orbital, the 3p orbitals, the 5d orbitals, the 7f orbitals, and the 9g orbitals. And if we are looking at the total number of electrons in each main energy level, the formula is 2n squared. So 1 squared is 2. That is the maximum number of electrons in the first main energy level. 2 times 2 squared is 8. That's the maximum number of electrons in the second main energy level. 2 times 3 squared is 18, which is the total number of electrons in the third main energy level. 2 times 4 squared is 32, which corresponds to the maximum number of electrons in the fourth main energy level. And 5 times 5 squared is 50, and this refers to the maximum number of electrons in the fifth main energy level. Now, it will be difficult for us to distribute electrons following this pattern because they're very difficult to remember. So the chemists came up with a device like this, which will help us in determining the order of filling up of orbitals. So we follow the down arrow. Notice that you have, for the s, each of the main energy levels will have an s orbital. From the second main energy level onwards, you will have the p orbitals. From the third main energy level onwards, you will have the d orbitals. From the fourth main energy level onwards, you will have the f orbitals. So we start with 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and so on and so forth, depending on the total number of electrons to be distributed. So all you have to do is know how to construct this device when you do electronic configuration. Now let us look at some examples. So if we were to look at hydrogen 1H1, that means hydrogen has 1 electron. So its electronic configuration will be 1s1. And if we were to do an orbital diagram, it would be this upward arrow for the electron. Now class, remember that each orbital can only hold a maximum of 2 electrons. And if we were to do the electron dot structure for hydrogen, it will be something like this, where you have the nucleus. There's 1 proton in the nucleus, and then around the nucleus you have 1 orbital, and that contains the 1 electron represented by 1 dot. If we look at helium-2, we will see that it has 2 electrons, and this is its electronic configuration is 1s2. Its orbital diagram will be this one, where you have an upward arrow and a downward arrow. You have the 2 electrons represented here in the s orbital, in the 1s orbital. Moving on, we have lithium-3. So notice that lithium has 3 electrons, right? So its electronic configuration will be 1s2, 2s1. Its orbital diagram will be this one, where you have the 2 orbitals, the 1s2 with the 2 electrons, and the 2s1 with the 1 electron. So that if we draw the lithium atom, you would have its nucleus here with the 3 protons, the 4 neutrons. You have 2 orbitals, the first one representing the 1s2 with the 2 electrons, and the second one representing 2s1 with 1 electron. Moving on to beryllium. Beryllium-49 has 4 electrons, so its electronic configuration is 1s2, 2s2. its orbital diagram is this two here, two boxes here representing the orbitals. And if you were to draw the atom, you have here the nucleus with the four protons, the 5 neutrons, and you have two orbitals. The first one representing 1s2, and you have the 2 electrons there, and the second orbital representing the 2 electrons in the 2s orbital, and it would look like this. All right, so I will stop here, and I will give you now a chance to work on the worksheet that I will give you. Thank you.